Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning, everyone. It's a great pleasure to have Daphna Shachaf here from Carnegie Mellon and Stanford, who's going to talk about the aha moment from data to insight.
Thank you. Okay, first of all, can you hear me? Excellent. So I'm Daphna, and like Eyal said, I'm going to be talking about my recent project, the aha moment from data to insight. So what does it mean? The thing is, there was a time not so long ago when getting your hands on good data was really, really difficult. Like this poor interviewer here that had to ride a horse across the country and ask farmers how many cows they had. And of course, today it's a completely different story, right? There you have this. Basically, cows, they tell you where they are and what they've been up to today. So getting your hands on data is no longer much of a problem. We have more data than we know what to do with. And this is actually great news for everybody, right? Because large-scale data has potential to transform almost every aspect of our life, from science to business and sport and public health. And it can really address some of society's most pressing problems. The thing is, for this potential to be realized, it's not enough to collect this data, to acquire this data, not even to search through this data. You have to actually understand it. You have to make sense of it. You really have to turn those heaps of data into insight. Okay, and this is where I come in. And my goal is to develop computational approaches for this problem of turning data into insight. And these are just some of the questions that I'm most curious about. Okay, for example, what is insight? Or given lots of data, how do you help people understand the structure? Or what are the most interesting bits and pieces? And ultimately, how do you use those ideas to build a system that will facilitate discoveries? Okay, so let me give you an example. And this is going to be in the context of news. So here's the scenario. Suppose you're trying to understand a really complex news story. Okay, the Greek debt crisis or the presidential campaign. So what do? Well, most of us would go to a search engine, right? We love search engines. Thing is, search engines are great at retrieving those nuggets of knowledge, but they won't show you how those 57 million results fit together, right? There's absolutely no structure. Now, I'm being slightly unfair here because there has been a lot of work on incorporating structure into search results, including work that came from here, like News Junkie. But most of it boils down to a timeline. Okay, like this is about a Greek debt crisis. And I'm going to claim that this style of summarization really only works with simple stories that are linear by nature. And that real stories are nothing like linear. Okay, if I had to come up with a picture of the Greek debt crisis, then it's not a single line. It's more like this. So what do you do with this spaghetti type of stories? Let me show the Holy Grail. How many of you have seen issue maps before? Okay, that's kind of what I expected. So this is an issue map. It's a set of 7 posters about the great AI debate about whether computers can think. Okay, let me just zoom in. It's basically a graph where each node is an argument, like machines can have emotions. And edges tell you that this argument is supported by that argument, which is disputed by the other argument. Okay, so you're really supposed to look at it and get the big picture. Now, I stumbled upon those issue maps at Carnegie Mellon, and it's a topic that I absolutely love, okay, one of my favorite topics. So I just stood there for an hour and read through the whole thing. And it finally made sense in my brain. Finally, everything clicked together. So I immediately started jumping up and down like, okay, great, so how did they make those beautiful creatures? And turns out it took them 20 man years, and they did pretty much everything manually. So my next question is like, okay, great, so how do you build those things automatically? Okay, making sense? Good. So issue maps are complex creatures, so I'm going to start simpler. And the system I propose is called metro maps. Okay, so your input is a set of documents. You can think about them as the result of a query, okay, documents about the Greek debt crisis. And the output is a metro map, where a map is a set of lines. Okay, so each line is a sequence of articles, and each line follows a coherent narrative thread. Okay, so this one tells you how the Greek bonds are rated junk, and they have to come up with austerity plans to get a bailout. And you have different lines that focus on different aspects. You might have another line about the strikes and riots triggered by the austerity plans, and another line about Germany. Okay, so you're supposed to look at it and really get both the temporal dynamics and the structure. So what are the major storylines and how they relate to each other? Okay, good. So how do you come about finding those maps? So anyway, finding a map is a really hard problem because it's very intuitive. If I show you a good map, then you know it's a good map, but why? So what I do first of all is start on this intuitive level, so just what makes a good map. For example, each storyline is coherent. But coherence is this really fuzzy term, so how do you formalize it mathematically? How do you come up with an objective function, something computers can play with? And once you have an objective function you're happy with, everything interesting I do tends to be NP hard. So how do you optimize it? How do you come up with an algorithm with some guarantees? Okay, making sense? Start intuitive level, what are properties of a good map, formalize them, and find a way to optimize this objective. Okay, so let's start. Take a couple of seconds and just think about it. So what makes a good map? Well, I guess I gave you the first thing already, right? It's coherence. So each line follows a coherent narrative thread. But what does that mean? So luckily we had an entire paper about this question in KDD 2010, where the question was, given a chain of articles, how do you measure the coherence of a chain? Okay? And I asked this question about coherence to a whole bunch of people, and they always come up with the same answer. Okay, oh, it's a really, really easy question. Just make sure that you have strong transitions. Okay, the D1 is similar to D2, document 2 is similar to document 3, 3 to 4, and you're good to go. And the entire point of this paper was that strong transitions are not enough. That coherence is not a property of local interaction between neighboring articles along the chain. Let me share what I mean. So those bars here means that the word on the left appears in the article above it. Okay, so this is an article about the Greek that crisis. Now suppose you want to build a coherent chain. So first thing you do is you try to find a second article that's similar to the first one, and you might come up with this. What the Republicans think about the debt crisis. Now if you completely forget about the first article and you try to find a third one similar to number 2, you might come up with this one. What the Pope thinks about Republicans. Okay, and you're just going to keep drifting farther and farther away. And you see this staircase behavior? It really means that you get a stream of consciousness here, that each transition is strong, but because of a completely different reason than the other transitions. Okay, so the overall effect is incoherent. Okay, let's try again. Same document, Greek debt crisis. Same second document, what Republicans think about the debt crisis. But this time you know where you came from, and you know that Republicans are not the main point. So you'll keep finding things that are on topic. Okay, and you consider the overall behavior is much smoother and nicer. You don't see the staircase behavior. And most importantly, there's a small number of words that can capture the entire story. Okay, so let's try formalizing it. First thing we want for a chain to be coherent is we want each transition to be strong. Okay, so this means we need to define a score for transition. First thing we did, super simple, a transition between document DI and DI plus 1 is the number of shared words. Okay, just sum over words, score 1 point if it's shared. Super simple. This was way too coarse, because first of all, some words are more important than others. And also words are kind of noisy features, so you might have an article about judge and jury, but not lawyer, so is it really implicitly there? So we really had to replace this indicator function with a softer notion that we call the influence of word W on the transition between documents DI and DI plus 1. Okay, and intuitively, this influence is high if both documents are related, and W plays an important role in what makes them related, even if it doesn't appear in either of them. Okay, and I'm not going to go deep into how we did this, but just to give you the flavor, so we made a bipartite graph between documents and words, and we looked at random walks between DI and DI plus 1, and then we looked at the same thing when you're not allowed to go through word W, okay, and see how word W actually affects those random walks.
Can I ask a simple question?
Yeah, sure.
How are these documents selected?
Think of a query. Okay, you have a query, Greek that crisis, just pick document. Oh, you mean the document of the chain?
Yes.
So at this point I'm asking about, given an entire chain, how do you measure the coherence? Later we're going to talk about how to find actually a good chain.
Okay.
Okay, good. Okay, so this was the score for single transition, and since you want all of them to be strong, then you really want the weakest link to be strong. Yeah?
You said you didn't want to go into too many details.
Yeah, sure.
But so one side of the bipartite graph was words.
Words and documents. Documents.
Documents.
So an edge means that a word appears in the document, and you can weight by TF-IDF.
And how do you do the walk?
Okay, we should probably talk about this offline, but the idea is just a random walk with random restart that's relatively high, so it's short walk, so you don't get too far away. And then you look at the random walk from DI, just back and forth through the words to DI plus 1. And then you do the same thing with W, it becomes a sync node, so it gets trapped until the next restart. Okay, we'll talk about it later. Good. So you want the weakest link to be as strong as possible. This means that all of the transitions are strong. Okay, good. So now we have that all transitions are strong, but what about, I just told you about there has to be a global theme, you can't allow the stream of consciousness, there needs to be a small number of words that captures the entire story, right? So we turn this into an optimization problem, actually find this small number of words that captures the entire story. Okay, so suppose I give you a budget. You're only allowed to pick 3 segments, okay? And I'm going to pretend that these are the only words that appear in the documents, and score just like before, but only using those words. So if you pick those 3 segments, there's nothing between document 1 and document 2, right? So your weakest link is 0. But if you pick those 3, then your weakest link is much, much better. Okay, so instead of summing over all the words, you sum over words that we call active. And the problem becomes just an optimization over activation patterns. Okay, so we look at the way to choose those active words subject to constraints that are trying to mimic this behavior of coherent chains. Okay, breathe in, breathe out. This is our notion of coherence. And the way we solve it was using an LP and a rounding algorithm.
So the
Yeah.
documents are ordered,
Yes,
and there's
by chronology, by the way.
predetermined- Okay.
Mhm.
So how do you get the order? I mean, it seems
Timestamp.
it's a whole big thing.
No, it's news article. They
It's
all have
news.
timestamp. By the way, I've been.
News stories come out at different times. You can have a news story that appears later that describes earlier events.
Yes. I was actually wondering about it. Later I'm going to talk about this for books and movies, and I was wondering if I can do...
The most coherent.
So it
Maybe
seems...
using the word differently than you are.
So as far as I'm concerned, if the news, or even if it came out later and talks about something earlier and still follows this behavior, then people will still get something from reading it in order.
So you need to determine when the events took place in the article that...
No, I'm just using the timestamp. It seems to be okay. I was worried about this, like in books where they have flashbacks. But this seems to be good enough even if the articles are not entirely if the timestamps are not completely matching the time of the event. Okay? That's the assumption. We can argue about it, yeah.
What's the definition of max over activations?
So it's which words you want to pick to be active, which segment you pick.
The maximum is to make them all active.
No,
Surely the
subject to
maximum is to make
constraints
them
that appeared here that are basically you have a budget of how many you're allowed to do. Okay, good, yeah.
Maximum over all subsets of the words of a
Yes.
certain size.
I may be stretching the example, but the Greek death prize got written up in English, in German, in Greek, and maybe in Turkish. And how do you deal with these documents? Now, it's not only normal human languages. Life insurance salesman will tell you last survivor, and you will understand second to die. And same with diplomatists.
Yes, so first of all, languages, we're only focusing in English right now, especially exactly because of this. Now, I was worried about using words, a part of the goal of this project was to see how far you can push really stupid features, named entities, noun phrases, and see if I actually have problems, if I need to use more sophisticated NLP tools. It didn't seem to be a problem. Okay, not yet. Good, coherence. So we have the first property, coherence. And at this point you should be asking me, so great, so are we done? Can I just pick the top 3 coherent chains and call it a day? So let me show you what happens when you actually try to do this. Okay, so your query is Greek debt crisis, and those are the top 3 coherent chains. Okay, so there's one about Asian markets and 2 about the strikes and riots. And so, what's wrong? Well, really 2 things are wrong. First of all, I have a budget of 3 lines, and Asian markets are not really the most important thing that was going on, right? There's so many more important things like what Germany was doing. And also the bottom 2 lines are redundant. There's really no reason for the map to include both of them. Okay, so the challenge seems to be balancing coherence with what I call coverage. Okay, the map should be about diverse topics that are important to the user. Okay, so what does that mean? So let's formalize it. Coverage. So first of all, I keep calling it coverage, so let's talk about the elements I'm trying to cover. And you can think about them as words. Okay, so Obama and China. So we have a probability that each document covers each word. And this can be based on TF-IDF. One more thing that we have is a weight for each word, for how much we care about covering it. And if you don't know anything, this can be based on frequency. Everybody's talking about Obama, he might be important. But this is like a perfect place to plug in personalization. If you do know something about him, like they don't care about politics, but they love sports. And what I said in the earlier slide was that high coverage maps should be about important things, and they should encourage diversity. And diversity just means some modularity, right? It has this intuitive diminishing returns. So let me show you how this works. Okay, so this is our corpus. The size of the words corresponds to its frequency. And we have the documents covered words fractionally. Okay, so this blue document is lots about Obama and Washington, and these are important words, so you get lots of corpus coverage. And then you pick another document that completely saturates Obama and New York. So at this point, if you pick another document about Obama, you get pretty much no incremental coverage. So the objective should push you to pick another word that's important and hasn't been covered yet. Okay, let's formalize this. So each document of the map flips a coin, and with this probability, tries to cover a word W. Okay, now if all of the map documents try doing this independently, this is the probability that at least one of them succeeded. Okay, then you take this is kind of how much the entire map covers each word, and you sum over all words, and you weigh them by how much you want to cover this word. Okay, so sum over words, how much do I care about this word, times how much the map covers it. And this is our notion of coverage. Okay, now we have two things, coherence and coverage, and how do they play together? Now, hopefully I convince you with the Asian markets example that coherence is not necessarily, you don't want the most coherent chains in your map. It's more like a constraint. A chain is either coherent enough for you or it's not. And coverage is the thing that you're really after. Okay, so the problem becomes, find me a coherent map that achieves maximum possible coverage. Okay, let me show you what happens when you try to optimize this. You get this map. Okay, same query, Greek debt crisis, one line about strikes, one line about Germany, one line about IMF. They're all coherent, they're important, they're diverse. What's wrong? Oh, come on, you're all thinking that, right? It's not a map, it's a set of disconnected lines. And it's especially frustrating when you see this thing at the bottom that's about Germany and the IMF, and it should have been connected to the red line. Okay, so the last thing I had was connectivity. If two lines are related, then I want the map to reflect this. Okay, good. So there are many, many ways to formalize connectivity. We did a user study, see what people care about. And it turns out they got really upset when two lines were related but not connected, but they didn't seem to care much about how they were connected. One point, multiple points, beginning, end. So we started with some really simple objective, to encourage connections. Okay, so when two lines intersect, you score a point. Super simple, just sum over pairs of lines. If they intersect, you score a point. Now later on, we went with more complex objective, but this was our first shot. So we have three things now. Coherence, which is this optimization problem that we solve with an LP and rounding. Coverage, which is a sum modular function. And connectivity, that's a super simple thing that just encourages intersection. Okay, good. So how do they play together? So hopefully, again, like before, coherence is still a constraint. And now coverage and connectivity, ideally I'd like to optimize both. But if I show you a map that's super well connected about something you couldn't care less about, then you probably still couldn't care less about, right? So coverage is really our primary objective, and connectivity is our secondary. Okay, so the problem becomes, consider all coherent maps that achieve maximum possible coverage, and out of those, find me the one that's most connected. And this here is lexicographic optimization, so the first term is infinitely more important than the second. Okay, good. Let me just give you a brief overview of how we optimize this objective. So our input is a set of documents. Again, you can think of them as a result of a query. Now, I said that coherence is a constraint. So ideally, I'd like to enumerate all possible coherent chains that can serve as metro lines. But that's clearly infeasible. So what I do instead is I encode all coherent chains in this structure that I call the coherence graph. Okay, and the idea is that each node of this graph is a short coherent chain. And an edge means you can concatenate them and they remain coherent. And it's a transitive property. So paths in this graph correspond to longer and longer coherent chains. Okay? So I really encode all coherent chains as paths in this graph. Next thing I want to do is I want to pick k paths from this graph that, again, correspond to coherent chains, such that the underlying documents maximize coverage. Okay, I want to pick a high coverage map that's coherent. So let's talk for a second about finding a high coverage path in this graph. So if you think about it, the parameter is just find me a path of some length L, maximize the coverage of underlying articles, which is just a case of the more general problem of find a path of length L, maximizing some function of the nodes visited, which is luckily a well-studied problem. It's called the orienteering problem. And many smart people have paid attention to it before. So we use the algorithms of Chakuri and Pal. Since our coverage function is modular, we can use a modular orienteering algorithm. And it's a very nice recursive greedy algorithm with approximation guarantees. Okay, good. So just going back. So we have this set of documents. We encode them as paths in this graph. And then we use some modular orienteering in order to find a set of paths that are high coverage and coherent. Last thing we do, we have a local search step that tries to increase connectivity without sacrificing coverage. Okay? So let me just show an example of the result of this algorithm. So we started from this very simplistic map of the Greek debt crisis. Now that's the real thing. So I have one line about how Greece struggles to stay afloat and they need help, but is it enough? Another line about the strikes and riots, another line about Germany, and a tiny line about the IMF. Okay, and at this point you should always be staring at it and saying, well, okay, it's a nice picture, but is it any good? Like, how do you even evaluate those things? And evaluating maps is challenging, okay, because we don't have ground truth, we don't have a golden standard, and we can use all those surrogate methods from machine learning and data mining, but I'm going to argue that for what I do, then user studies are crucial. Okay, first of all, because I want to make sure that we capture those intuitive notions we started from, coherence, and also to make sure that what we're building is actually useful for somebody. Okay, I really want those maps to be useful. So let me tell you about the user study. So the question of the study was, well, can maps help news readers understand news events better than state of the art? Okay, so we had New York Times articles from 2008 till 2010, and I picked 3 queries: the miners trapped in Chile, the earthquake in Haiti, and the Greek debt crisis. Okay, and the question was, again, can maps help people understand those 3 stories better? So first thing we tried was really simple, just question answering. Okay, so we gave people 10 questions, like how many miners were trapped, and we measured how well they answered us and how long it took them using other maps, Google News, or something called topic detection and tracking. And we had roughly 340 users, and well, we're doing better than competitors, but nothing to write home about, okay, nothing major. And I was talking to people and I said, if I wanted to know the name of the Greek prime minister, I would Google it, I would go to Wikipedia, this is a complete overkill. And they're absolutely right. So I think what we learned is that maps are not about those small things, about those control F type of search, they're really about the big picture. So we needed to design another study to see if maps help somebody understand the big picture. Now, how do you know if somebody understands the big picture? So, okay, if you taught a class, you should know what I'm talking about. You only understand something if you can explain it to somebody else. That's what I think. So what we did is we asked people to look at the maps or look at Google News and write 1 paragraph explaining the story to somebody who has absolutely no idea. Okay, then we took those paragraphs, we put them on a mechanical Turk, pairwise evaluation, double blind, and asked people, so which paragraph does a better job explaining the story? Okay? So I had 15 paragraphs writers, write roughly 300 evaluation per task. The results were much, much better. Okay, for the Greek debt crisis, we had 72% of the people preferring paragraphs generated by map users. Now, it didn't look as great for Haiti. We're under 60%, and I was curious about why. And I went looking at the actual paragraphs. And turns out the Haiti map had one major storyline, there was an earthquake and damages and efforts, and a couple of tiny lines about what was it, Wycliffe Jean running for presidency, or missionaries accused of kidnapping children, something like this. And pretty much everybody that summarized this map just focused on the one major storyline. Okay, so I think that the bottom line is that maps are the most useful as high-level summaries, just as like for stories, they don't have a single dominant storyline. Yes?
So the people doing the evaluating, do they know anything about the topic beyond what a random person knows? I mean, do they already know about the topic, or are they just...
So this is mechanical Turk with like slight quality control, they have to know English and they have to have...
Someone who's okay,
no.
So it's just...
Yeah.
I mean, well, one could argue that that's a flaw, right? Because, I mean, it's just a paragraph that is appealing and appears to be helpful to a non-expert.
Yes, one could totally argue this, and I was talking about this a little bit in the paper, but it seems like a reasonable baseline. Okay, good. So, I tried to convince you that maps are good for news. And my goal for the next few slides is to tell you that maps are not just about news. Okay, that in fact they're really, really easy to adapt to other domains. Because the main principles, coverage, coherence, connectivity stay just the same. But you might be able to use domain knowledge to come up with a slightly smarter objective. And I'm going to talk about 3 examples of science, legal documents, and books. So let's start with science. So the goal of this project was to see if maps can help somebody understand the state of the art of some field. For example, what's reinforcement learning been up to? And the data we had was ACM papers, and we needed to do some slight modifications to the objective, mostly taking advantage of a citation graph. But other than this, the algorithm stayed exactly the same. Okay, so let me just show an example. So this is a map about reinforcement learning. I don't actually expect you to read it. Let me just walk you through it. So there's one line about the multi-agent setting, one line about MDP, POMDP, one line about controlling robotic arms, one line about bandits and exploration exploitation, and a line about bounds and theory. And by the way, you see that those are actually disconnected, but there's those funny dashed gray lines between them. That's because in the scientific domain, you might have a line about theory and a line about applications, and there's really not a single article that can fit in both, right? There's no direct intersection. But those lines are clearly related. There's lots of citation going on between them. So in the scientific domain, we allowed for indirect connectivity. Okay, so if two lines have lots of impact going on between them, then we count this as well. So this lets us see stuff like, how the serial line had impact on the bandit line, or how the MDP-POMDP line had an impact both on the robotic arms and on the multi-agent line. Okay, let me tell about the user study, because this was a fun one, actually. So the question was, can maps help somebody, a first-year grad student, understand the state of the art, okay, of some field better than current things? So what we did, we brought people in my office, and we told them, pretend to be a first-year grad student who's kind of embarking on a reinforcement learning project. And you go to the professor, you're all excited, you want him to teach you everything he knows about reinforcement learning. And the professor gives you a survey paper. Only problem, this paper was written in 1996. Okay, so the goal is really to update this survey paper, to find the more recent research directions and relevant papers. And they could use either Google Scholar or maps in Google Scholar. Okay? So we had 30 participants. We basically combined all papers into one long list. And we had an expert judging precision, okay, so which papers are relevant, and subtopic recall. So we composed a list of the top 10 sub-areas of reinforcement learning in the last years, and we wanted to see how many of those areas they managed to find. Okay, so just in a nutshell, the result, on average, the map users had 10% more of their papers deemed relevant, and out of those top 10, they managed to find on average almost 3 more. Okay, so at this point, we were very happy. One more thing I want to do in order to convince you that maps are a good idea for science, we actually made a map of our own related work at some point. Okay, so this is us from connecting the dots to metro maps. And again, I don't want you to read it, just to see what's been around us. So lots of work on summarization, especially news. Lots of work on narrative. Some work on coverage notions. This pink line about visualizations like concept map and mind maps. And this red line about mapping science. Okay? Good, third thing we did, legal documents. Okay, so there was a company in Palo Alto that came knocking on our door one day. They do a search engine for lawyers, and they wanted to know if maps can help a lawyer argue a case. So they gave us Supreme Court decisions. I don't know, have you seen Supreme Court decisions before? You might have, no? So the problem is that they're insanely long. Okay, they can be hundreds of pages. So my TF-IDF was completely not finding signal in those. So it turned out that was working is that when you cite another case, you have to say why you're citing them. Okay, so in blah versus blah, they define that Commerce Clause applies here. So if we just use this anchor text to kind of pinpoint us to the most interesting parts of the document, then everything else falls just beautifully into place. Okay, let me show you an example. Just one map we computed for them for a Commerce Clause. You can see, for example, this purplish line about who can waive state immunity, and if you work for a state-owned company, can you sue them? Okay, great, how about in federal court? And okay, great, does this section apply or not? So we basically showed this map to the lawyers to get a reality check. And they first of all said that it made perfect sense. They were even nice enough to label each line for us. And then we went ahead and computed the words that made this line coherent from our point of view. Okay, so you can see, for example, the third one. The lawyer said the 11th Amendment, state sovereignty. We said immunity, sovereignty, amendments 11th. Or the last line, regulating wholesale energy sale, and we said wholesale electricity resale steam utilities. Okay, so they've been happy about this. We're probably integrating it into their search engine now. Okay, last thing I did, this was just for the fun of it. I wanted to see if maps can help somebody understand the structure of a complex book. And when I say complex book, I actually mean Lord of the Rings. Okay, mostly because I refuse to read a Song of Ice and Fire until he actually finishes writing it. So we had Lord of the Rings, and there my biggest problem was coherence. Okay, think about it. Journalists are really nice because they actually tell you what happened before. Okay, but books don't really work this way. They don't say, okay, now that we're done with the battle at Helm and this guy's dead, we can go in and do that. They just, go in and do that. So coherence was completely breaking. So what we decided to do was say, well, hopefully a single character's point of view is a coherent narrative thread. Okay, so focus a lot more on named entities. And let me just show you a detail from the Lord of the Rings map. So you see that the hobbits and Gandalf start walking on their merry way. They collect people all the way to the council, and then they split up. And you see Pippin and Merry going somewhere, Sam and Frodo going the other way, they meet Gollum, the bad guys are down there and they're going to eventually meet the good guys. So there's lots of structure already emerging. Okay, one more thing I want to tell you about what we did recently to make maps even more useful. So first thing I was worried about was scalability. Okay, I really wanted to handle web scale corpus. So we basically revamped the entire objective. Everything I used to say was embarrassingly parallel, we actually made parallel. And we came up with a hierarchical, like clustered version of metro maps, so each metro stop is not just a single article anymore. And we brought it down from 11 minutes on 7,000 articles to 30 seconds per query on hundreds of thousands of articles. Second thing I was worried about was interaction. Okay, and I really think it's going to make or break metro maps, because I'm not going to nail the right map based on a couple of keywords. So, but on the plus side, I mean, maps allow for so many awesome interaction mechanisms, right? So we tried two things. One that they call multi-resolution, where you can zoom in to learn more, or zoom out to get a high-level overview, where the most interesting technical bit was we had to come up with a community detection algorithm that makes this really non-standard assumption of dense overlaps. Okay, so we had a metric factorization algorithm with some block coordinate and gradient descent. Second thing we did was word feedback. So remember in the coverage slide I told you this is a perfect place to plug in personalization, those weights. So we actually had a mechanism that lets people say stuff like, okay, I don't actually care much about what Germany was doing, but oh, Portugal is interesting. And the map would recompute based on whatever I think is important to them now. And we use ideas from UMass, okay, from Andrew McCallum's group, something called feature-based feedback. Last thing I think that I did this semester, and this is a really fun project with a student, is thinking about controversial topics. Okay, so suppose you look for something like Obamacare. So there's really not one map, right? It's really more, Democrats versus Republicans. So we looked for how to formalize this notion of controversy using polarizing sentiments, and how to kind of cluster documents based on their sentiment and compute two different maps representing two different points of view. One more thing that's been going on. We have a website, very final stage of GUI debugging, and I have a student whose entire mission for the quarter is to come up with an open source package, so people can plug in their data and see what comes out. Okay, so this has been a really, really exciting semester. Now, okay, so metronomes, the entire point of this project was to take a newsreader or a first-year student or a paralegal or really anybody that has lots of data and needs to rely on search. And we want to show them a perspective of their field, okay? We want to show them the structure and how things connect to each other. And we talked about how to formulate this, coherence, coverage, connectivity. We had an algorithm, and we have used the study to validate our idea. Now, at this point, I was kind of staring at this and trying to think what to do next. So what don't I like about metro maps? And the thing I dislike the most is that maps will only show you connections that are explicitly made by somebody. Okay? A journalist told you that those two things are related. But what if you want to make new connections? Okay? What if you want to discover something new? So this is how the AHA project came to life, where the goal was you have lots of data, how do you find something insightful in it? Or really, how do you define this fuzzy notion of an insight? Okay, so just a word of caution, this is work in progress. It's a lot less mature than metro maps, but I have been having so much fun with it, I thought I'd tell you some. Okay, so the goal is to define insight. Now there's been lots of related work about this, right? There's psychology, cognitive psychology, there's data mining. I mean, you can argue that the entire KDD is about taking data in and getting insight. Same thing for lots of the InfoVis conferences. And I was basically going through a lot of papers and trying to abstract those ideas. Okay, so what makes an insight? Okay, so just like before, what makes an insight? Okay, first thing is almost trivial, right? It has to be surprising. If you know about it, then nobody cares. But surprise alone is not enough, because if, give me enough data, I'll find plenty of things that will surprise you, just because they're noise or bias or coincidence. So it has to be what I call plausible, or really well supported by the data. Okay, and this is a super general idea. So let me just show you how this plays out in the medical domain. Okay, now the medical domain is perfect for me, because there's lots of data just lying around, and every day you see those articles about researchers found a link between blah and blah. So there's a potential for many, many new links to be discovered. Because we wanted to use this idea to build a system that will kind of take researchers and give them some promising research directions. Okay, so identify where the gaps in our current knowledge. Okay, so we said plausibility and surprise, and how does that work? First of all, for the purpose of this presentation, I'm only going to restrict myself to a really simple kind of insight. It's a pair of medical terms. Okay, like there's a connection between sleep apnea and diabetes that I think is insightful. Okay, so just a pair of medical terms. Now, for something to be plausible, I need this to actually co-occur a lot in practice. Okay, so many sleep apnea patients actually do get diabetes. And in order for this to be surprising, you go to the literature, and nobody ever thought about it, or nobody ever noticed it before. Okay, so we look for pairs of things that co-occur a lot in practice, but nobody in the literature seems to know about. Okay, so what kind of data do you need in order to compute those things? So for plausibility, we had 70 years of hospital notes. Okay, natural language just notes, we have about 10 million of them. And for surprise, we have 11 million papers from Medline. Now, this is an overview of the system. And if you lost me, by the way, this is a good place to catch up. So we have a system. It starts from a query. Now, it doesn't actually have to start from a query, but researchers usually have something they care deeply about, so let's start from a query. In this case, sleep apnea. So what the system does, first of all, it goes to the medical notes and looks for plausible candidates. Okay, so what happens to sleep apnea patients in practice? Then you take those candidates and you rank them according to midline. So what's surprising? Okay, so sleep apnea, what happens in practice, and what does the literature not know about? Now for this to work, I need to tell you three things. So where are the terms coming from, what's plausibility, and what's surprise? Okay, terms. So we extracted the medical terms from the notes and from Medline. And first of all, this was a lot more annoying than I expected. Okay, because it's natural language, so physicians might tell you sleep apnea, acute sleep apnea, recurrent sleep apnea, and this was completely messing up my counts. Okay, so I need to know when I can merge something and when I can't. So we decided to use medical hierarchies. Okay, so we have this kind of thing. This is SNOMED, I think. You have stuff like migraine disorders that has two children, common migraine and not so common migraine. And you really want to know when you see something, whether you can merge it up or not. Okay, so what we decided to do was use KL divergence. So compute how much information is lost when you use a parent in order to approximate a child. And you can see, for example, that if you see common migraine, you can propagate it all the way to migraine disorders, maybe even vascular headaches, depends on your threshold. But if you see this other type of migraine, no, it's a completely different beast. Okay, now surprise. One or two things surprising. Well, first of all, they can't co-occur together too often, right? So we have a threshold. So the number of papers mentioning them can't be over K. But that's still not good enough, because there might be two terms that just don't appear because nobody cares about them, right? Because 5 people in the universe combined have them. So it's more surprising if those terms are popular, okay? If nobody knows there's a connection between sleep apnea and diabetes that are really well researched. So we have, just like before, we have weight, so the importance of a term. And the way I like thinking about this is it has novelty and it has utility. Okay, so this is surprise. Now, plausibility in a way works exactly the other way around, right? So two things should co-occur together in practice a lot. So what we did was we aggregated all the notes that a single patient received in a year. Okay, that's our basic document. And the first thing we did was just compute a really simple Jacquard coefficient. So how many patients have both those things over how many patients have at least one. And let me just show you what happens when you try to plug those two objectives into our system. Okay, so we start from dementia. Those are the top 6 Jacquard coefficient things that happen with dementia. So the first 3 are Alzheimer and 2 medications used to treat dementia. So they're going to be filtered away by Medline. But then you're left with hip fractures, atrial fibrillation, and wheelchairs. And at this point, you should get really suspicious and say, well, hip fractures, wheelchairs, we might have a problem here. Right? Because it might not be about dementia. It might just be that this population tends to be old. So we needed what I call explanatory power. Okay? And I'm trying not to say the word causality, but you can think about it this way if it helps you. So the idea was we took a group of people that are really similar to dementia patient, but don't have dementia. Can we use propensity score matching to compute this group? And then we said, well, hip fractures, are they a lot more common for dementia patient than for this other group that's just really similar but doesn't happen to have dementia? And if it's not, then you're not capturing the right thing here. Okay? It's not about dementia, it's about them being old or something else. So plausibility is about having high Jacquard and also about passing this matching test. Okay, so let me just show you what happens. You start from dementia. Now wheelchairs and hip fractures don't even pass the test. And the only thing you're left with is atrial fibrillation. And they spent out, okay, so what do you do with it? Is it an insight? Again, how do you evaluate? And ideally, I would make just a series of bold predictions and send an army of physicians to chase them down, but this requires time and money and physicians, and I don't quite seem to have either of those things. So instead, what we did was early discovery. Okay, so we asked physicians to give us a list of the breakthroughs of the last 5 years, and then we time traveled on the data and say, well, if you had run this algorithm 5 years ago, what could I have told you? And specifically, what would show up in the top 3 results of my search engine? The idea is that if you can predict anything, it's a really strong indication you have something. Now, I said it was really preliminary. They only gave us 4 things. Okay, obesity and colon cancer, diabetes type 2 and sleep apnea, atrial fibrillation and dementia, and incretin and pancreatitis. But out of those 4, we actually managed to figure out 2. So physicians are much more happy and they're a lot more willing to cooperate with me right now, and they promise to give me a much longer list. Okay. Now, by the way, I started by saying that this is a really general idea. So I want to show you how the exact algorithm, the exact formulation works in a completely different domain. Okay, and this is the commerce domain. So the idea is to get a search engine that encourages serendipity. Okay, here's the way to think about it. Suppose I want to buy a laundry hamper. Okay, then I don't actually want a laundry hamper, I need a place to store laundry. So what the same idea of an algorithm does is find products that are plausible, in the sense that they solve a similar problem. And they're surprising in the sense that when you go to Amazon, people who view this, then nobody in their right mind who is looking for a hamper would consider this other product as an alternative. Okay, so I have a search engine that says, you don't need a laundry hamper, how about you buy a really big trash can? And by the way, I was telling this to a friend of mine, and he said that he uses a trash can for a hamper, and I was so happy. But anyway, my entire point here is to tell you that the algorithm is just the same. Just instead of medical note, we use ConceptNet in order to learn common sense facts. What are things used for? And instead of Medline, we use Amazon. People who view this graph. And everything else is just the same. Now, I thought that if I already tell you about it, I can give you some shopping tips from, playing with my algorithm, just in case you want to buy something. So here are some things I learned. First of all, at least in this country, pet products and baby products are surprisingly interchangeable. Okay, it just keeps showing up. It's scary. Also, you might want to look up at the car department every now and then. Okay, so here I was looking for, the thing you put in a bathtub in order not to sleep, and cars really have the same thing. And also, by the way, the system said, forget the idea of a mat, just buy stickers that people put on the staircase, again, in order not to slip and fall, which made perfect sense to me. Okay, the AHA project. The point was that medical researchers, I really wanted to give them a tool that will let them discover some promising new ideas. And we formulate the surprise and plausibility. We have this early discovery of some medical breakthroughs. And I didn't quite talk about there are so many applications in other domains. Okay, so we talked about this product search, but there's also something called literature-based discovery. There's also, we did this through Wikipedia, lots and lots of places where this could work out. Okay, this seems like a good place to take a step back and try to understand what we had here. So I talked about two projects, the Metro Maps and the AHA project. What's the common thread? What's the underlying common theme? So I guess the obvious answer is this idea of turning lots of data into insight. But there's really more. Okay, so the problems I like the most are the ones that start with this really intuitive problem definition. Okay, so what's a coherent storyline, or what's an insight? And then you formalize it mathematically, optimize it, and then tie it back to a user study. Okay, both to make sure that you capture the right thing, and to make sure that your system is actually useful for anybody. I really want to build those things to be useful. Now, in order for this to work, I basically borrow ideas from data mining and machine learning and information retrieval, lots of algorithms, especially optimization and graph algorithm, and some HCI and visualization. Okay, this is what comes in. What goes out is I try to apply this in as many domains as I can. And today I talked about medicine and science and news and legal documents and commerce and literature. Okay, good. So this is what I do. Let's talk about what I want to do next. So first of all, I'm in the Insight project. Again, it's super preliminary, and we're really excited about this idea of building a set of tools that will allow anyone, okay? So scientists, analysts, really anyone, just plug in their data and see what's the most insightful thing that comes out. And really to enable some new discoveries. And again, I want to stress out this importance of finding a technique that generalizes across domains. I really think it makes the technique much stronger. Okay, so I talked about some of the applications that I already tried, and let me briefly tell you about the collaborations I've been mostly excited about recently. So first of all, I gave this talk at the Stanford Computational Social Science Conference, and there's been all those social scientists and political scientists just came to me afterwards carrying awesome buckets of data. Okay, so there's Congress notes and crime data and lots of really beautiful data sets. Life sciences, I really wanted to apply this to biology. I don't actually know how, so if you know anybody who might be interested, you know where to find me. History, okay, there's a history professor who really wanted to apply this idea of metrograms to telegrams. Okay, personal data is something I've been dying to do for a really long time. Okay, so search browsing history. Because suppose you're trying to plan a trip and you find yourself an hour later with 75 tabs open in Firefox. And wait, what just happened? So really a way to kind of organize your browsing history into some structure. Okay, what else? There's been some interest from corporations about corporate data, financial data, this idea of insight for investigative journalism. And the last thing on this list actually really surprised me. Okay, I never thought this would work for anything that's not text-based. But recently, some researchers at UT Austin applied my algorithm to summarize a video as a sequence of images. Yeah, no, you just under this. So anyway, so apparently this thing also works for images. Again, really surprised me. Okay, so this was short term. Long term, like I said, I really like this idea of taking fuzzy things and formalizing them. And out of those, my favorite by far is this thing here in yellow, this creativity. And I know it sounds kind of megalomaniac, so let me just tell you briefly about one thing I started doing this semester about it. Okay, so just 2 slides. So the goal is you own a company, you own a product. Okay, you have the technology and you want to change your product in order to expand your business. So what should you do? And we follow this thing called the scamper model. That's basically a set of questions you should be asking yourself, like, what can you combine your product with? How can you put it to another use? How can you reverse some functionality? My favorite example, this company that used to make water pressure shower heads, and now they're making water pressure dental floss, which I just thought was completely brilliant. Anyway, my point is I built a prototype system using the same ideas of ConceptNet in order to answer those questions, and Amazon to filter out the obvious things. Now I have a search engine where you type in something like alarm clock, and it just spits out suggestions like combine it with a coffee machine. So you wake up to a fresh cup of coffee. Or combine it with a dimmer so the room kind of becomes lighter and lighter as you wake up. Or maybe make a silent alarm clock, something that vibrates. Either for deaf people or if you don't want to wake somebody else up. Anyway, I just keep spitting and spitting suggestions. Do you know SkyMall? The thing you get at airplanes? So I think I'm roughly at their level right now, but hopefully it get better soon. Okay, good. So, breathe in, breathe out. The point of this talk was we have plenty of data, and this is excellent because data can help us understand the universe and make better decisions. But it's not enough to collect this data or to even search through this data. We really have to make sense of this data. Okay, we have to reveal the structure, like in MetroMaps, and we have to eventually discover unknown connections, like the AHA project. Okay, we had those user studies, and we have early discovery to validate our ideas. And if there's one thing I want you to take from this talk, it's probably this image right here. Okay, we really have to go beyond just searching our data. That's about it. Thanks. Awesome.
Any questions?
So I have a question because you were saying that the people who looked at the metro maps didn't care so much about the relations that might hold between the nodes on the map. Is that because you are drawing the map at a document level?
It might actually be. I'm not entirely sure why they're doing this, but this was pretty clear from the data. We showed them 2 things that were related, and they could intersect at the beginning or at the end. They did say that something was ugly if they just kept bouncing on and off. But other than this, they didn't seem to care much. And I'm not sure why, actually.
When you do medical discoveries, it
Oh,
probably will be more
Yes.
important.
that I completely agree.
That's what I was thinking. And I wonder if you move this to the sub-document level.
So I really wanted, the issue maps I did at the beginning, they have a node as an argument. And I just don't know how to get this, how to abstract. But hey, we're going to have a meeting and talk about it, right? Excellent. How does it work? And people who are watching it online, do they have any way of asking questions?
They can run downstairs. They can
Wait, hold the button.
Yeah, I've seen it. Bursting through the door.
So when you were measuring the number of active words in the coherence
Yeah.
part, how did you set the threshold? Because the more words you have, the less effective it becomes. But,
Yes,
right?
the more words I have, I can actually go back to the staircase behavior,
Yeah.
right? Because each transition is going to have its own budget.
So how did you put the threshold?
Oh, so we just tried it on a couple of stories that were not used for the user studies, and we just manually tweaked this. Again, eventually, I would love to learn this, but this was just tweaking parameters.
Did you do some experimenting with, what you did was select a threshold and then treat all these words equally? You just summed over the number, over the active words?
So summing, for every active word, we summed over the influence of this word on the transition. So it's not just 0,
Yeah,
1.
but then you cut it after 3 or 5, which was your thread, as opposed to just some.
Yeah, we didn't let them die. We also, it's an LP, we can just not rounding. It would still work.
Any other questions?
If we have a lot of data, and how can we use your project? So
Excellent.
being
I would say email my student and bug him, but you should probably email me, so I'll bug him. Yes, but he was supposed to finish it a couple of weeks ago. It's probably going to take him a couple more, but it's almost ready. Well, now I'm curious, what data do you have?
actually, I think we have a lot of data. We're just trying to find a way and using the data, finding insight. So right now we're still at the level of the collect statistics.
Mm-hmm.
And yeah, we want to move forward, and this is very interesting.
Bring it on. I'd like to try this.
Sorry, have you published the work on the medical discovery?
So Yuri wants it to be a Nature paper, which has been taking me longer than any other paper I've written in my life. If you want, I can send you a draft.
But so which hospital were you collaborating with so that you could get the patient
They don't
reports?
actually tell us, but I'm pretty sure it's the Stanford Hospital. It's a Stanford medical group. It's either this or the Palo Alto Hospital.
Because that's an amazing data set.
70
Usually
years.
they have no I mean, like I've worked with data sets with, at most 500 patients, and that takes like 2 years to get access to. So that's an amazing data set.
Stanford medical team has been awesome about this.
Yes.
Okay, let's thank the speaker again.